My name is Nikhil. So we're here to talk about machine learning in JavaScript with TensorFlow.js. So if you're familiar at all with machine learning and data science, you'll know that most of it happens in Python. So this is a poll that was given by a popular data science blog called Katie Nuggets. And you can see that Python absolutely dominates. And this is for a pretty good reason. There has been many, many years of tooling built in Python for data science, from NumPy to Pandas to scikit-learn to TensorFlow. And this field is going to continue to evolve in Python. And I don't have to convince the folks in this room, JavaScript is a very, very popular language. This is obviously the Octoverse survey by GitHub, and you can see that JavaScript absolutely dominates. So we think that there's actually a lot that the JavaScript community and the folks in this room can bring to machine learning. So who here has seen this? This is TensorFlow Playground. OK, a few people, but not a lot of people. So I definitely recommend checking this link out. This is an in-browser visualization of a neural network. It was built by one of our colleagues at Google. And the idea here is you can immediately change the number of layers, neurons, learning rate, and so forth, and immediately see how the neural network generalizes over a data set. Now, this thing was a huge educational success. It's being used in universities across the world now in Google's own machine learning crash course. So again, I definitely recommend checking this out. So we stepped back and we kind of asked ourselves, why was this such a success? Like, why do people care about this in-browser machine learning thing at all? And we kind of distilled it down into a few points. So the obvious thing is that you can just click a link and you get going. If you've done any Python ML, it's like really pain in the butt to get your drivers installed, Python libraries installed, and that kind of thing. It's super interactive. You have buttons, you have hyperparameters that you can play. You can immediately see how changing the knobs affect the learning configuration of the model. We didn't take advantage of this in the playground, but in the JavaScript world, in the browser, you have cameras and microphones and standardized access to these things, which you don't really get as much in the Python land. And super important to us is that you can actually make predictions locally, and data can stay on the client. So this is privacy preserving. So we took this and we launched a library called TensorFlow.js. We released it last year in March. It's GPU accelerated, so we use WebGL to make everything fast. So we actually do all the linear algebra in fragment shaders. And I'll talk a little bit about that in a second. But one of the things that we do is we let you make predictions through machine learning models, but we also let you train them directly in the browser or even in Node.js. And we'll talk about that as well. So when designing the library, we had a couple goals in mind. One is that we wanted to empower a diverse group of JavaScript developers like the folks in this room. There's a lot of really awesome people in this community, and we want to sort of marry these two worlds. At the same time, we wanted the folks who are experienced in the machine learning to be able to port their work to the web. Now, these goals are kind of sometimes at conflict, so we'll talk a little bit about how we resolve those. OK, so one of the principles that we had was we wanted the library to be super easy to use, and we kind of leaned towards that over performance. At the same time, we didn't want to sacrifice any functionality for simplicity. So just jumping into what that means, we decided to go with this eager-only approach. I'm not going to go into what that means, but it's a much simpler way of programming, and actually most of the machine learning world is moving towards this eager approach. Versus a graph-based approach where you actually stitch together a computation graph and execute it later. And we really want it to be easy, so we moved towards eager. We also provide a high-level layers API, which is a set of best practices in the machine learning community, so you don't have to think about all the details of your linear algebra when you're constructing a model. And we also provide a whole repository of pre-trained models that require zero understanding of machine learning to get started. And I'm going to show you a couple examples of those in a second. And I want to highlight this. We focus on performance when and where it matters. Obviously, we want matrix multiplies to be fast. What we did was we took individual models, and we figured out how to make those individual models faster on a use case basis. So as I said, we don't want to actually make the library less functional. So we support gradients. This is fancy talk for sensitivity of each of the weights, which means we can train through any operation that you use in the TensorFlow.js library. We support a lot of the TensorFlow ops, 130 of them. And for any of these models that we're about to show you, you can actually dig down and get some of the machine learning constructs out of them if you want to. OK, so quickly jumping into what the technical stack looks like. At the very top of the abstraction APIs, we have our models repo. So this is a set of pre-trained models. I'll show you a couple of those in a second. Require very little understanding of machine learning. Below that, this is our layers API. This is where you can construct a model. You can train the model. You can serialize the model for later. And we'll show you some of that soon, too. And we also have below that our core API, which is just linear algebra kernel. So these are matrix multiplies, convolutions, and their gradients, which are derivatives. So all of these APIs, you can sort of poke in at any of these abstraction layers. All of these sit on top of WebGL in the browser. We use fragment shaders to run all of our math in parallel. And in Node, we actually bind with the N API to TensorFlow C++. And what that means is, if you use that same API for any of these things, you immediately get the hardware acceleration that TensorFlow has been working hard on for the CPU and for GPUs with CUDA, and eventually we're going to have TPU support. It was also very important for us not to silo ourselves in the JavaScript world. There's a whole wealth of models that are trained in the Python ecosystem that we want to take advantage of. So we have converter tools that let you take a Keras model or a TensorFlow saved model and bring them back into the JavaScript world. OK, so let's quickly take a look at what the models repo looks like. So if you check out this link, these are all our pre-trained models. These are hosted on GitHub and on NPM. So we host all the weights and all the JavaScript for you. And we have a wealth of models, from object recognition to human pose detection to localization to segmentation to text classification. And the list goes on. Just go check this link out. But I want to show you one of the demos, because it's fun. So there we go. OK, so this model is called PoseNet. It's running completely in the browser. Nothing is being sent back to a server. And the idea here is we take RGB images from a webcam. We pass it through this pose detection model that generates key points for each of sort of my body parts. And then it returns an object that we can just render on the screen. And obviously, it works with 2 people. So this is a lot of fun. And we'll show you how to use one of these models in a minute. The second model is very similar to PoseNet. It's doing person segmentation. So it's, this background's a little funny, but basically what it does is it draws a mask of a 1 where it thinks there's a human pose and a 0 where it thinks there's not. So this one's a lot of fun, and I don't know if this is going to show well here, but one of the effects I really like is portrait mode. You can see this thing blurring. So we have a software-based portrait mode that's running directly in the browser pretty fast. OK, so let's go back to the slides, and I'm going to show you how that actually works and what the code looks like. So that model is called BodyPix. It's a pre-trained person segmentation model that we've done a lot of work to make super fast. Pretty straightforward. You import TensorFlow.js and BodyPix, 2 libraries. We have them on NPM. We host them on CDNs for you. We have a regular image tag. That's it. And this image is Frank. Now, Frank is Nick's baby, and he is doing a yoga pose for us. So we're going to try to figure out where Frank is in this image. So first, we just load the model. We call await bodypix.load, and this is going to download all of our weights. These weights we host on our GCP buckets for you, so you don't have to pay for any of that. And then you just call 1 line of code, estimate person segmentation on the image, and you get a JSON object out. And inside of that JSON object is a binary mask of where it thinks the kid is. It's that simple. You don't really have to understand the ML bits of this. One of the other things this model gives you is parts as well. So it'll tell you which pixels are face, which pixels are arms and legs, and so forth. And we provide some fun utilities for drawing masks on top of those. So you can imagine this being used for like a video game sprite. You just jump around on screen, and you immediately have a fun video game sprite. OK, so I don't have to explain this to the people in the room, but JavaScript runs in a ton of places. And we're working hard to get TensorFlow.js working in those places. So we have the browser and Node, obviously, but working on Electron and React Native and WeChat. So we'll talk about those in a second. But I want to show you some of the cool examples that we like in these worlds. So on the browser side, hopefully the links are here. We have a project called Creatability. This is one that's done by Google. And it's a set of experiments around, can we make interacting with music and art more accessible? So we're using that PoseNet model that I showed you, and we're actually able to play a synth with just our face. And this runs completely in the browser. The link is there. Go try this after the talk, please. Cool. So then we also have a project called Uber Manifold, not by us, by Uber. And this project is a way to debug and understand machine learning models as they're training. And they actually use TensorFlow.js just for linear algebra, so fast matrix multiplications in the browser. Airbnb is also using TensorFlow.js. They ship a little model to the client. So when you're about to upload a profile picture, if they see a license or a government-issued passport in that photo, they'll yell at you before they upload it to their server. So they don't have to own that PII on the back end. On the desktop in Node, there's a project called Clinic Doctor, and Clinic Doctor is a project that monitors your Node application for CPU spikes. And they use TensorFlow.js actually to disambiguate garbage collection spikes from your CPU in your actual program. One of my personal favorites is a project called Magenta Studio. Magenta is a team at Google that does generative music and art. And they actually have an Electron app that plugs directly into Ableton Live. And it can generate MIDI notes on a track for you, or it can generate a drum beat alongside maybe a guitar groove that you have. So this is a ton of fun, and it augments an existing workflow. And JavaScript is awesome, so of course we do it there. OK, so this other platform called WeChat is massive in China. If people don't know about it, it's got 1 billion users, lots of mini programs, lots of developers. And they all run on JavaScript, and we're working hard to get GPU acceleration stories working inside of that. With that, I'm going to hand it off to Nick to talk about some other stuff.
Thanks, Nikhil. As we kind of highlighted, JavaScript runs in a lot of places. And we're starting to think of areas where we can keep expanding where you can run TensorFlow.js. I want to step back and talk about our node bindings first before we dive into the next topic. We launched these about a year ago. And the library is great because it's super fast. It uses that C library, like Nikhil mentioned. And it's great for deploying onto servers or doing local workflows on your desktop or workstation. But there are a few downsides of this particular library we have. One of them is the GPU acceleration requires NVIDIA's CUDA library. It's a really fast library, but it's very large. And we at TensorFlow don't currently support Mac OS, so there's no GPU acceleration on Mac. And the other thing is the node package itself is a native module, all built on an API, and it links to the C library of TensorFlow. That can be really large depending on which library you're using. CUDA can be around 250 megabytes or so just on Linux. So it's a very large package to ship. So we started to think, is there something in between we can do on Node? And we started working really hard and launched earlier this year a new headless graphics stack for Node. And we launched it. It's called the Node-GLES package. We worked hard with the Chrome team here to build a headless graphics stack for that. And we wanted to take that and accelerate our existing WebGL stack, all headless in Node. And this library runs by Angle, and Angle is the driver we ship in Chrome today. And it translates WebGL calls to your native system graphics stack. So on Windows, it's Direct3D, OpenGL on Windows, and then your native macOS graphics stack implementation. So we think this is going to be great for some desktop apps like Electron, mobile and embedded space, and then IoT devices. Plus, this is going to bring GPU acceleration to macOS. We're working hard to finish this up, a couple of things. So we're hoping to launch here later in June or sometime this summer. And I wanted to show a demo of this actually running. We built a really quick Electron app. So if I go ahead and just run my app, this app uses MobileNet, which is one of our out-of-the-box models that does basic image classification. So you can see an image and tell you what it is. So as I pull up in my app here, not the most exciting UI, but it shows the GL stack that's running. You can see it's running Angle with an OpenGL 4.1 core and the latest OpenGL ES stack through Angle. And when I click Run Demo, what's happening is it's going out, it's fetching our model, it's loading, and it predicted that that's a Labrador retriever, and we're running about 150 milliseconds, or I'm sorry, we're running 150 predictions on an image, and are averaging about 23 milliseconds. So that's very close to 30 frames a second in real time. So we think this is going to be really great. On the Electron side, it doesn't block your UI thread for doing all the displays. You're dispatching all these ML calls through the Node process, all with a headless GL. and that package is like 5 to 10 megabytes. It's very small. And I also wanted to show one other thing. This is the latest type of IoT boards. This is a NVIDIA Jetson Nano. And it basically just has a big GPU stapled to the top of it. And we were able to, last week, get this running with this headless stack as well. Running that same model, a Node console dump isn't that most exciting, but we're doing around 76 milliseconds of inference time just with the very thin ARM64 build of our Node backend. I also want to talk about another library we've been working really hard, and it's in-browser visualization for our TensorFlow.js library. So we launched this package. It's called tfjs-viz, and you can think of it as like the Chrome dev tools for ML models. We have this thing called the visor, and it slides out, and it's a canvas for painting a bunch of elements that the library provides. We have a bunch of built-in charts, such as loss and accuracy for ML training. We also have what we call high-level visualization methods. This basically allows you to look at those complicated ops like convolutions, which do a bunch of filters on your image while you're training and see what's happening in between each of those convolutions. Model evaluation utilities is another set of drawing libraries, and that sort of shows you where your model is, might be over-biased to a particular class, and ways that you can sort of see how you might alter your data set to make sure you have a very nicely trained model. All right, we've shown you a lot of stuff, but we want to show you a lot of the things that Nikhil, myself, and the team have been thinking about and where we're going forward with the project. One thing is we're really excited about the current future with all the new specs that are coming down the browser, especially with JavaScript. On the website, we have 2 new standards we've been looking at really hard the last couple months. One of them is WebGPU. WebGPU is the next generation graphics stack that's coming to the browser. We've been working really hard with the Chrome team to try to get that implementation up and rolling. Another one we've been looking at is WASM. Now, in the ML world, we really need to do SIMD to make WASM a really effective accelerator for CPUs. So we've been working really hard on that, again, with the Chrome team, and we're hoping to have something for devices where the GPU isn't all that great. We can fall back to WASM SIMD. One of the great parts about the ML space is just the amount of research. And we're finding about every year the same models we have get faster from reductions in architecture or new hardware acceleration stories. So every year, the models that we keep showing continue to get faster, especially on edge and browser devices. Another great product we have at Google is AutoML. And AutoML solves the whole training part if you want to do an image classification problem. You can give it a set of images, and it uploads to the cloud, and it automatically finds the right architecture for your model, and then spits out the model that you can deploy on your device. We're looking at some integration with that team as well to make it just a real seamless experience. And the other thing that our team has been focusing on is just optimizing our existing backends. So our WebGL implementation, for example, we worked on packing textures, which is a fancy term of using less memory as much as possible in our acceleration library. And we found that sped up a bunch of things, including iOS, up to 10 times faster than what we were seeing before. Looking at the things we're going to launch this summer, visualization is already launched. Another package that we didn't really highlight is the data library. And the data library is just a real easy-to-use package for getting stuff out of the browser. Microphone data, webcam data, you don't have to worry about converting to tensors. You can just sort of streamline these things into your model. On our platform side, expanding where we run TensorFlow.js, as mentioned, WeChat, the headless WebGL stuff, and then we're really starting to dive into how we can provide a nice React Native experience. And then on our out-of-the-box model fronts, we're going to continue focusing on audio and text models, as well as improving the accuracy and performance of our existing offerings. With that, I want to thank you for attending our talk. Everything we've shown is we work purely in open source, and all of our stuff is found on js.tensorflow.org. One of the other things we wanted to acknowledge is while Nikhil and myself work at Google and we get to work on this project would not be where it's at without the large number of open source contributors we've had, and we want to extend a thank you to them for all the hard work they've done. And then one last plug, we are actually hiring a developer advocate for our team. And if anyone is interested, please follow that link or come see us at the booth here at JSConf. And that's all.